Every hydraulic machine you'll encounter has exactly one job: converting the energy of moving fluid into mechanical rotation. Engineers use two distinct methods to achieve this. This split-screen diagram illustrates the divide between impulse and reaction turbines. Looking at the left side, the impulse turbine relies completely on kinetic energy. A high-speed jet of water strikes the blades directly. The entire process happens under normal atmospheric pressure, meaning there is zero pressure drop as the water moves across the runner. Contrast that with the reaction turbine on the right. Here, the machine uses a combination of kinetic and pressure energy. The runner is completely submerged and enclosed, forcing the water to push its way through. This creates a continuous pressure drop from the moment water enters the turbine until it exits. Now that we have the baseline mechanism, we can map out the structural framework. This flowchart classifies every turbine type you are required to know for the AEE exam. The specific machine an engineer selects depends on two main variables: the available head, categorized as high, medium, or low, and the flow direction, which can be tangential, radial, or axial. This categorization framework guides site-specific selection. Because each turbine is engineered for a specific range of fluid forces, matching the wrong machine to the available head and flow can result in a runner that vibrates or fails under the weight of the water. Let's closely examine the Pelton reel. This diagram illustrates its tangential flow. Notice the central splitter in the bucket. When the high head jet strikes, the fluid deflects by 165 degrees, transferring the maximum momentum to the wheel. Moving to reaction machines, this graphic breaks down the Francis turbine, a mixed-flow device. Follow the arrows to see water entering radially inward, then turning to exit axially downward, all under a continuous pressure drop. Next is the Kaplan and propeller family. This schematic shows a pure axial flow path designed to handle massive water volumes at very low heads. The distinguishing feature for the Kaplan was its adjustable runner blades, keeping efficiency high even when flow drops. To measure performance, we use this hydraulic efficiency formula. It often creates a calculation bottleneck. However, if exam problems specify purely radial discharge, the outlet whirl velocity becomes zero. This collapses the complex equation into a single simple multiplication problem. Identifying that specific geometric condition reduces the calculation to a 30-second task. It resolves the efficiency question quickly, allowing you to move through the remaining problems without wasting time on dense algebra. Reaction turbines exit water below atmospheric pressure with wasted kinetic energy. This requires a draft tube. Notice the expanding cross-sections on the right. Increasing the area forces water to slow down, converting leftover kinetic energy into useful pressure energy before safe discharge. Once a site is evaluated, engineers use this specific speed spectrum to pick the right machine. It is the exact numerical metric calculated to determine whether a dam requires a Pelton, Francis, or Kaplan turbine before construction begins. Separate specific speed from unit quantities, detailed on this dashboard. Unit speed, discharge, and power are strictly for an installed machine. If a drought lowers the reservoir head, we use these exact formulas to predict how the turbine's performance will change. Operating machines involve strict physical limits. Look at the danger zone. If the external load is suddenly disconnected while water flows, the turbine accelerates instantly to runaway speed. This absolute terminal velocity generates massive centrifugal stresses. Another danger comes from the fluid. Reviewing question 1.2 on this document, cavitation pairs directly with vapor pressure. If internal pressure drops below vapor pressure, the water boils. The resulting bubbles collapse violently, carving metal chunks out of the blades. Plant design is an active balancing act. You optimize theoretical efficiency equations while ensuring the physical hardware stays safely away from destructive limits of runaway speeds and cavitation. Let's put this into practice. A site has an output of 9,000 kilowatts, a working head of 25 meters, and runs at 150 RPM. Pause the video, calculate the specific speed, and determine which turbine type belongs here. Plugging the values into the formula gives us a specific speed of 135. Checking our spectrum, that places us squarely in the required range for a Francis turbine. Now consider what happens if a severe drought drops that 25-meter head by 50%. Because the turbine is already installed, we abandon specific speed and calculate unit speed instead. By isolating n, you calculate precisely how the RPM drops in tandem with the square root of the available head. To synthesize all of this, here is your capstone matrix. This table maps out every turbine against its operating head, flow direction, specific speed, and draft tube requirements. Take a screenshot of this layout now. Internalizing the data on that single matrix and remembering to check for the purely radial discharge condition will secure your marks in the hydraulic machinery section of the APPSC AEE exam. Keep practicing those problem sets, and we'll see you in the next module.